Hello and welcome to a discussion with Vladimir Dzhunushaliev regarding quantization of measure in gravitation. Vladimir was kind enough to present a presentation of his own for this discussion, so I hope you enjoy that very much.
Okay, so let me explain why this subject is interesting for me. So I know many attempts to quantize gravity. This is supergravity, string theory, and loop quantum gravity. And from my point of view, the loop quantum gravity is the best way to quantize general relativity. So, I am not expert in the loop quantum gravity, but when I tried to read some books, papers, I found that in loop quantum gravity, the guys can quantize, in fact, say quantize measure. What is it measure? Measure is, with measure we can measure the length, the area, the volume. So, in loop quantum gravity, there are very famous results that, for example, the area is discrete. So what is discreteness in loop quantum gravity? In order to obtain such a result, we have to triangularize this our space. So this is like this. So this is tetrahedron, and using some special mathematical tools in loop quantum gravity, we can obtain that these areas are quantized, are discrete, proportional to Planck length, Planck square, Planck cube for volume, and so on. Then, after some calculations, I saw that maybe it's possible to generalize such approach to understand how we can quantize measure in general case. So first of all, we have to understand what is the operator of measure. Why? Because let me come back to quantum field theory. In quantum field theory, the problem of quantization, for solving this problem, we have to quantize all physical quantities. The main paradigm in quantum field theory is that all physical quantities are operators. So, and in order to understand the properties of such operators, we have to write commutation relations. That is very famous commutation relation in quantum electrodynamics, in quantum chromodynamics, in standard theory model, in standard model, and so on. But for what is the problem here for measure? So measure is non-local object. Non-local object means that if we compare the situation with quantum field theory, in quantum field theory, the operators are the functions of point. For any point, we can define field operator. But measure is non-local object in the sense that we can define measure only on the some area. Here, for example, the measure of this tetrahedron is 1 or 2 square centimeters, and so on. So, and so this is a problem to write commutation relations for measure. So I think that is the main problem for such non-local quantities. And in our first paper, we suppose such commutation relation. So this is absolutely identical to quantum field theory, only in quantum field theory, here we have local object, here we have local object, and here also we have local object. So, and on this way, I think that it's possible to obtain very interesting results And for example, in loop quantum gravity, we have the result that the measure of tetrahedron of length, the area and volume are quantized. And in the second our paper, we try to generalize such commutation relations in the sense that so on the right hand side it's possible to write some integral of any physical quantity, for example R, which is connected with general relativity. R is sorry, I had some illness, so and
okay.
Sorry. So this is modification of our previous result in our first paper. And in this way, we can obtain very interesting interrelation between quantum measure and general relativity. Why? Because if we average this relation, so on the right hand side we will obtain some quantum averaged general relativity action. So, and in fact we have two problems. First problem, find quantum algebra of such operators, and the second problem is to find metrics which will satisfy this relation. So if we average right hand side of this expression, so we will obtain this expression, and here we can use the principle of least action to obtain some effective equations. But what is the connection with general relativity? In general relativity we have this expression as the action of for general relativity. So, and now what is it average value of this equation? So average value will be maybe I want, let me so so we have such relation, commutation relation. On the left hand side we have some operator, here is operator, here is operator, and on the right hand side we have also some operator with measure. This is measure, and here is also measure. So we can generalize this expression to write here not simple measure on some object. For example, this can be surface or volume, but we can insert here some function. For example, function which is connected with general relativity. And if, okay, let me say that I want to connect this problem with problem in general relativity. In this case, I have to write some equations for R. R is some function of matrix. And if I average this expression, I will obtain that on the right hand side I will have such an expression, and averaged measure. So now, sorry, we can use Radon-Nikodym theorem. So what is that Radon-Nikodym theorem?
First of all, why do we want to use that? And why are we trying to write the commutation relationships in this way? So you said
Yeah.
before that they have some commonality to the action that we have in general relativity. And when we have the integral here, I agree, there's a commonality between the two. Why is that important here? How does this help us? This rewriting of the commutation relations when it comes to quantizing the measure or the measure in gravitation.
The answer is very simple. So, do you see my screen?
Yes.
So, if I write this equation without R, so this is commutation relation from loop quantum gravity. So the question is, it's possible to generalize such expression? The answer, yes, we can generalize this expression without R, and generalization we can write in such form. So why I want to generalize usual commutation relation from loop quantum gravity? So I want to, the main goal of my research in this direction is explain the relation between quantum gravity and modified gravity. So what is it, modified gravities? Modified gravities is a modification of general relativity. So, and at the moment we have many applications of modified gravity. For example, to explain what is it, dark energy. So dark energy is some physical explanation for modern accelerated expansion of universe. You know?
Yeah. Yes.
Yes. Okay. So, and with modified gravity, it's possible to explain this accelerated expansion of universe. So, but the problem is that modified gravity is too much. We have for modified gravity R square, Starobinsky modified gravity, and so on. That's too much. We have too much theories, and it's necessary to understand what kind of modified gravity we have in our nature, in our universe. So my opinion that if we use quantization measure in quantum gravity, we can explain how some kind of modified gravity can be obtained in different physical situations. The idea is that in one physical situation, for example, near to Big Bang, we have one modified gravity. Close to the singularity of Schwarzschild black hole, we have another modified gravity, and so on. So, but the question is how modified gravities, one of the set of modified gravities is related with quantum gravity. So, in this approach, so I can show that if we have such commutation relation for such non-local object as measure, we can obtain modified gravity. So let me explain how we can do that. First of all, let me write quantum average of this expression. So on the right hand side, I will have such this expression. So, but this expression is proportional to the action from general relativity. Only one difference is that I have averaged measure. And in general relativity, we have such action R square root minus G and d theta, dt, dx, dy, dz, and so on. So, of course, quantum averaged measure and this measure which is associated with metrics are different. So, d mu, or maybe, d mu averaged is not equal measure which is associated with metrics. But I can apply Radon-Nikodym theorem. The Radon-Nikodym theorem tells us that any measures are connected with some kind of function. So it looks like this. If I have two arbitrary measures, mu and nu, then we have such proportionality. This f is some function, some non-negative function. So I can use this theorem to connect averaged measure and measure with, okay, maybe better to write d mu, which is associated with matrix. And this is some function. So, but in this expression, in this expression, we have R. So I have to introduce here R. So R d mu is equal R function f and metric which is associated measure which is associated with matrix. But of course this function is scalar function, depends on coordinates. F is scalar, but x mu is vector. So only one way to obtain scale from vector is that f depends only on R, or maybe Ricci scalar square, or maybe Riemann scalar square, and so on. So immediately I see that on the right hand side of this expression we have R times f, which depends on, in the simplest case, R. So this is the called modified gravity. And here it might be R cube or everything. So this is I think that this is very important consequence, that if we have quantized measure, then approximately general relativity with such relations gives rise us to modified gravity. So from my point of view, this is very important because we have relation between modified gravities, which are very interesting object in modern theoretical physics, and quantum gravity. In fact, in this case, we have two problems. First problem is a definition of algebra of operators of measure. So this is commutator is equal, and here something we can write something. This is first problem. The second problem, from this we can obtain something, maybe we can say that averaged general relativity equation which are modified gravity. But of course, this equation will be approximate description of quantum gravity in some physical situations. So maybe, so I can assume that, for example, close to Big Bang we will have some one kind of modified gravity. Strictly speaking, close to Big Bang we should have some we can apply only quantum gravity. Close to the singularity for Schwarzschild hole, we have to apply only quantum gravity. But if we try to have some approximate description, we can use such modified gravities which are coming from such series of my steps. So this is why, for me, quantum measure is an interesting object for further investigation. Even more. So, of course, we have question. Is it possible to obtain some practical results coming from quantum measure? Maybe it's possible in such way. So let me consider any standard field theory, Maxwell theory, or maybe Young-Mills theory. So that means that weak or strong interactions. So in order to write equations for example, for Maxwell theory, we have to write such action. So this is Lagrangian for Maxwell's electrodynamics. That's square, some combination of electric field square minus magnetic field square, something like this. But here I have to write averaged measure. Again, using Nikodym, Radon-Nikodym theory, we know that this averaged measure is connected with measure associated with vectors in such a way. So, and now, if I remember Radon-Nikodym theorem, I have modified Lagrangian for standard field theory. For example, in such a way, we will obtain modified Maxwell theory. Of course, this F is very close to unity. So this difference between Maxwell theory and such modified Maxwell theory is very small. We can write modified Maxwell's equations or Young-Mills equations or any other equations and then calculate what will be the difference. And it's possible to measure such difference in some experiments. For example, maybe in Hadron Collider or I don't know, maybe some astrophysical experiments. So, but here, so this difference, I'm sure that this difference will be very small. But at the moment, we did not such calculations, and I don't have any estimation how much is or how small is this difference. So unfortunately. Mm-hmm. So nevertheless, I found in the literature papers of Sergei Sushkov, for example, so he considered such modified Maxwell's equation. So that it was said in my previous slides. So this is, it is the Sushkov considers scalar fields, not Maxwell's equations. Phi is some kind of scalar field. F mu is some combinations of metrics and tensors, scale curvature, Riemann, Ricci tensor. So, and he found interesting consequences. Here, as I remember, he obtained many expanded universes with some several steps of expanded universes. So, nevertheless, it's possible to do such calculations with modified field theories. Okay, so
what does it conceptually mean for us when we use the Radon-Nikodym theorem to change the measure? So fine, we can apply this function and do a change of measure, and then the commutation relations that we showed before get a structure that's more or less equivalent to the structure in general relativity. What does that change of measure conceptually tell us? What does that represent?
So, in my opinion, if measure is quantized, then classical general relativity will be modified in such a way that we will obtain modified gravities. Stravinsky gravity, I don't know, R-square gravity, and so on. And in the same way, we will obtain modified classical field theories. Of course, such modification will be very small in the Earth, but such modification can be very big, close to the singularities. So this is the consequence of Radon-Nikodym theory, because in Radon-Nikodym theorem we have some additional factor connecting between averaged measure and measure which is associated with metrics. So the main property here, this is this coefficient f. No, okay, so so maybe better to say what is most important from my point of view. For me, the most important is that we have some bridge between quantum measure and modified gravity, because modified gravity can explain accelerated expansion of universe without any kind of dark energy. It is very interesting. This is in this case we have geometrical explanation of modern accelerated expansion of universe. So this is, for me, this is very interesting. First of all, second one is that it's possible to assume that maybe quantum measure will smooth the singularities. So what that means? That means that we have many singularities: cosmological singularity, Schwarzschild singularity, and I want to propose, I can suppose that close to singularity, of course, we have to use quantum gravity. So, and maybe the main problem to solve such problems with singularities is that we have to use we have to use quantum measure. Why? Because maybe close to singularity, this factor between quantum measure, averaged quantum measure, and measure associated with metric will be very big. And this factor, for example, in Weyl gravity, this factor has not any sense, because in Weyl gravity is conformal equivalent. Conformal invariance means that physical situation when we multiply volume on the any function is irrelevant. So situation will be the same. So probably this factor f, which is connection between two measures, maybe will kill singularities in Big Bang singularity, or maybe in Schwarzschild singularity. No, it's only assumption. I don't know. So this is and third, my conclusion, which is I think is mostly interesting, that we have, I don't know, so quantum gravity is very complicated mathematical problem. So maybe in some cases we can use approximate some simplification with modified gravity to obtain physical result without any singularity. So, and approximately the space-time close to singularity, maybe we can obtain this description of space-time close to singularity, we can obtain with modified gravity. Briefly speaking, that I can assume that quantum gravity close to singularity can be approximately described with modified gravity. So I think that is most important in this direction, working with quantization of measure.
Okay, great. Is there anything else you would like to say to the community before we close? Any sort of asks from the wider research community or anything like that?
No. Then no.
Okay, then very good. Let's end it here. Thank you very much, Vladimir, for taking the time to speak to me.